Not a trace put out in my mind. I'm in love. I'm a believer. I couldn't live.
Good morning. All right. So we are going to pick off where we left off on Wednesday, talking about ketones and aldehydes. So as a bit of a review, when we're talking about alcohols, ethers, ketones, and aldehydes, we're talking about how proximity to your electronegative atom, like your oxygen, is going to change your shift. So for this first one here, we're talking about ethers. These carbons are directly bonded to this oxygen here. It's a single bond to an oxygen, and they show up in this 3 to 4 ppm range. We move over to this ketone here. We have our carbon that is attached to our ketone in the middle. It is a double bond to an oxygen. It doesn't actually have any protons on it, so it doesn't give a shift at all, which is usually a sign that you have a ketone if you have a carbon that has, or an extra carbon when you're looking at your formula up here. As well, these two that are one carbon away from this C double bond O are going to show up in this 2 to 3 range. And this is going to be pretty universal for anything that's next to a carbonyl, whether it's a ketone, an aldehyde, a carboxylic acid, or an ester. So looking over at this aldehyde here, one away from our carbonyl, is in the 2 to 3 range. And then our big giveaway that we have an aldehyde is if we have something in this 9 to 10 range, this is directly attached to the carbon with the double bond oxygen, which really is going to shift it and put us in this 9 to 10 range here. So I left you guys with the next two problems to do yesterday or this morning. So looking at this here, we have a signal that's in the 2 to 3 range, which is most likely next to a carbonyl or some sort of a double bond. We have an oxygen. Taking a look at our integrations, we have 4H, which we haven't really seen before. This generally responds to 2 symmetrical CH2s. And then we have 6H, which is going to be 2 symmetrical CH3s. And this is going to actually give us a different example of symmetry. So we have some sort of probably a ketone based on what we've seen so far. Put that into teal. So starting with that, our 2 to 3 range should be attached to the ketone. So putting these two CH2s on either side. Two would give us this here, and then throwing. So looking at our peaks, we have 4 peaks, which means it should have 3 neighbors. So it should have a CH3 on either side of this, which is going to be our other 2 symmetrical CH3s. So this is a little bit of a different example. Normally when we think of these like symmetrical CH2s, we think of them as being like a branch chain like this. It can also be if you have something like this here, where you have a really big symmetrical molecule, you still have a giant plane of symmetry that goes through here. So these 2 peaks are going to be identical, as well as these peaks, because you could just kind of like fold them on top of each other and they're still symmetrical. If you have something that like breaks that, so if you had this is going to change everything now. None of these are symmetrical. You don't have to worry about that. So it's just kind of in this rare case where you have a symmetrical molecule, you can end up with a different type of symmetry here. Okay, aldehydes are really straightforward. It's a peak from 9 to 10. It's always a peak from 9 to 10, so it's easy to identify. This is an aldehyde. From here, you're kind of just doing what you've normally been doing. So CH2, CH, 2 CH3s. Identifying our peaks. So this is 3, should have 2 neighbors. 3 should have 2 neighbors. I believe this is a 9, should have 8. And this is 2, should have 1 here. So next to our carbonyl should show up in the 2 to 3 range. Should have 2 neighbors. It's going to be this CH2 that's in the 2 to 3 range. It's supposed to have 2 neighbors. Currently, it has 1 from the aldehyde, so a CH would make sense. And then our CH is supposed to have 8 neighbors. Currently has 2, which means it needs 6 more, so 2 CH3s. We could go through and label this one. So A, B, C, D. A is going to be our aldehyde. B is going to be our only CH2. C is going to be our only CH. And then D would be these 2 CH3s here. As we start getting into multiple oxygens, so now we have O2 here. There's 2 different options. We can either have carboxylic acids or esters. I'm only going to talk about carboxylic acids right now. When we do the carboxylic acid and ester chapter, we'll kind of go back and do some more examples. I'm just kind of giving you guys a crash course. And then when we actually get into the specifics of these exams, we'll go back and review them a little bit. So a carboxylic acid, something I really didn't talk about last time is that the actual alcohol signal there's this guy that's next to it, that's in the 3 to 4 range. But your OH itself actually has a pretty big range. It can show up between 2 and 7. So anytime you see that weird little like flip guy, it doesn't have to be between 3 and 4. Your little OH peak can kind of show up anywhere it really wants to. But if it ends up really far down, like in this 11 to 12 range, this is going to be a carboxylic acid. So if it's all the way down here, this is going to be a signal that what you have is going to be this. Also in your book, they give you like a table that says where all these show up, and I'm going to give you guys that in your exams also. If you look on the old like fall exams, you can see that it's already there. So from here, we do everything else like normal. So 1 next to our carbonyl should be in the 2 to 3 range. We can count some peaks here. So this would be a CH, CH2, CH3, CH3. I don't know what this is doing over there. 6 peaks, 5 peaks, 2 peaks, 3 peaks. So 2 to 3 range is going to be next to our carbonyl. It's got a CH. Supposed to have 5 neighbors, so a CH3 and a CH2. We've only got 1 CH2, so that makes things easy. That CH2 is supposed to have 4 neighbors. It currently has 1, so it needs a CH3. If we want to go back and label them A, B, C, D, E here. A is our carboxylic acid. B is the H from our CH, our only CH option. C is our only CH2. D and E are both CH3s. This first one is supposed to have one neighbor. So this CH has one neighbor, it's next to a CH. Sorry, this CH3 is next to one H. This CH3 is next to a CH2, so I would have two neighbors. So D is going to be this bottom one. E is going to be this top one here. All right, last topic I'm going to talk about in NMR is going to be aromatic rings. Anytime we are between 6.5 and 8, and you get a signal, it's going to be an aromatic ring. And for the sake of this class, it's going to be a benzene ring. So for this example, it's a 5H, which means of the 6 possible positions on a benzene ring, 5 of them are filled, which means we only really have one spot open here. Next to a benzene ring is kind of like next to a carbonyl. It's in that 2 to 3 range. There's a CH3 here. That's our only other signal. It's going to end up on our benzene ring and give us our product. I'm going to give you guys a few minutes to work through the top one on this page. There it is. And then we'll go through it together and switch gears and do some synthesis problems. All right, so between 6.5 and 8 is an aromatic ring. I'm going to start by just drawing my aromatic ring. It's got 5 protons on it. Which means it has 1 opening. Taking a look at the rest of what I have. So I have a CH, CH2, CH3, CH3 here. Between 2 and 3 is attached to my ring. So I'm going to throw this CH on first. Got 2 openings. It is supposed to have 5 neighbors. So in order to make that, I would need 3 and 2. I've only got 1 other CH2, so that has to be the one I just put on there. It's supposed to have 4 neighbors. It currently has 1. So throwing that on here should get me to my final product. For labeling this A, B, C, D, E here. A is just going to be this whole thing. B is going to be my only CH. C is going to be my only CH2. D is going to be my CH3 with 1 neighbor. So this CH3 is next to 1 neighbor. E is going to be the one on the other side, giving me this product. Any questions on these? Okay, so moving into some synthesis problems. Oh, what section of the book have we gone over so far? So someone asked me what section of the book have we gone over so far. So I believe we've done 8, 9, 10, and this is technically 15. All right, so synthesis. So I'm going to kind of do 2 of them, and then I'm going to give you some time and let you guys do a few of them on your own. One of them is going to be a little simpler. The next one's going to have, oh, you want to do that a little bit. Okay, so taking a look at this synthesis problem here. Typically speaking, what I like to do first, no matter what strategy I'm doing, is to try to fit my starting material into my product. So we have a 5-membered ring here. We have 1 carbon by itself, and we have 2, 3 for this triple bond here. Taking a look at this 5 carbon ring, 1, 2, 3 carbons. Most likely, this is going to be where our starter material fits into our final product. And that means I'm missing some carbons here. So I'm 3 carbons short on this. So at some point in time, I'm going to have to do an alkylation. I've got 2 bromines on here, which means I have to do a bromination at some point in time. And I don't have any sort of double bond, which means I'm probably going to have to reduce it at some point. So taking a look at some of the options, I'm going to kind of draw these out and talk about why I'm going to do an alkylation first. Let's do a spot I can grab it. So redrawing my starting material. If I do my alkylation first, so I throw in Na, NH2, the 3 carbons I'm missing, and the leaving group. That would get me to here. And at this point, I can still do a reduction and I can still do a bromination. I'm not really stuck anywhere. If I try to reduce this first, so throw in H2, platinum, I'm going to get this. And this is essentially a dead end. Unless I want to start doing radical reactions, there's not much I can really do with this. I can't alkylate it. I can't brominate it. I'm kind of just stuck with what I have. If I brominate first, so I add in Br2, I'm not as stuck. I could still reduce this down with H2, but I don't have a triple bond, so I can't alkylate. It basically gets me to here, and I don't have a way from getting here to adding carbons. So this is another dead end. And this is why I usually tell people if you need to alkylate, try to do it as soon as you can, because you're going to want to get rid of that alkyne at some point. And if you do that, you're not going to be able to alkylate again. So kind of taking this as our first step and going back to what we had before. Throwing in NaNH2, our leaving group. Someone asked if you should alkylate first, and every time you get to these type of synthesis, anytime, typically speaking, if you have the ability to do it, like I'll talk about one a little bit later where you have to make the alkyne first. But yeah, if you get to a point where you have an alkyne, do your alkylation. So from here, I want to end up with this at some point. It's probably going to be easiest for us to reduce first and then brominate. So if I do that, throw in, there's 2 different reduction reagents you could possibly use. You can either use H2 and Lindlars, or you can use sodium and NaNH3. So I'm going to draw the H2 and Lindlars pathway first. You'd make a cis bond. versus Na and liquid ammonia. From here, you could brominate both of these. So these both look like they work, but actually only this one does. I don't know if you guys talked about this when you talked about brominations last semester. If you brominate this versus this, so you're adding in Br2, if you want this to look the same as this, where this has like this zigzag carbon skeleton, you have to rotate this 180 degrees. So that would give you this, because when you rotate this, this one's going to get shifted to the front. You're just kind of like spinning it around that axis. But this is actually how you make syn BRs versus anti BRs. You just take a cis double bond versus a trans double bond. So taking a look back at this here, this looks like it's the right answer, but actually once you rotate it, this is going to give you, I want this the wrong stereo center. So in order to do this, you would have to come from a trans double bond and then do your bromination. So going back to our synthesis and doing this whole thing stepwise, the first step we're going to want to do is an alkylation. So adding in NaNH2, our alkylating reagent. This gives us the full carbon skeleton. We want these to end up being trans to each other. So we're going to make a trans double bond first and then brominate it. So NaONH3. Would give us this. And then we could throw in Br2. So that was a lot of work for 3 steps. You can kind of see how if you throw in the wrong reagents, you're going to end up getting the wrong products. So sometimes it's worth it to kind of work through things like this. There are some other things you can do. enter some different strategies. I'm going to talk about a different one, which is called retrosynthesis, where essentially we try to work backwards to find what our final product is going to be. I tend to kind of do a combination of the two. So if I'm asking to do a synthesis that looks like this, we have a couple of different options as to where to start. If we're doing a retrosynthesis, we're just kind of thinking, how can we go backwards? Like, what would make an aldehyde? And these are retrosynthesis arrows that go in the backwards direction. I don't know why they did that. Essentially, the only way we know to make an aldehyde is from an alkyne. So if we had this, we could get to there. And this is going to kind of somewhat be our starting point. We have to find a way to get from here to here. And I'm going to kind of walk you through a way to do this that works a lot. You guys are going to see it a lot. So to do this, we would want to have, there's really two different options you could have for this. And you're going to see why you're only really going to get one. So you probably want, I'm going to put BRs on there. Could be chlorine, something like that. Something where you can double eliminate to make an alkyne. You could also have this where they're both in the same one. The problem with this is that you actually need an alkyne to make this, so that's kind of redundant. Why would you make an alkyne to get rid of your alkyne to make your alkyne? So getting here, we're going to want a double bond. Here, and we can kind of work in between these two to figure out how to get there. So I'm going to kind of reference this a lot, but I'm just going to start by redrawing our starting material. So put this aside for a minute. This has nothing on it. It doesn't have any functional groups. There's nothing really you can do. The only reaction that actually works for these is either a radical bromination or a radical chlorination. And there are sometimes you're going to want to use a radical chlorination, but generally a bromination is going to work better. If we actually did the math, the chlorination would probably end up adding to one of these two. So I'm just going to throw in Br2 in light. This is generally a pretty good starting point if you're ever lost and you have nothing on your molecule. Throwing in Br2 in light will get you to steelbrominate at your most substituted center, excluding these quaternary centers. We can throw a Br on here, and now we're somewhat working towards something. So if I go back to this little synthetic diagram we had, we want to make this. So if I throw in a base, I'm going to get kind of close to that. I've got a double bond. It's just in the wrong spot. So for shifting double bonds, the easy way to do this is going to be through a peroxide mechanism, or not mechanism, but peroxide pathway. So if you throw in HCl and peroxide, HBr and peroxide, we can put the Cl in our last substituted center, and then throwing in a large base. We can shift it to what we wanted. So from here, we've got what we need. So looking at our diagram, we need to brominate, we need to make an alkyne, and we need to make an aldehyde. So we've kind of diagrammed out everything we need to do from here. Throwing in Br2 will let us dibrominate. Throwing in base will let us make our alkyne. And then finally, something like 9-BBN. Oh, wrong with answer. And H2 peroxide and NaOH. Will let us make our aldehyde product. So this was a lot of steps. This is 1, 2, 3, 4, 5, 6, 7. Generally on your exams, it's probably going to be about 5 steps. So I'm somewhere in between the first one and this one. But you can expect to kind of see these kind of things where you have to do either shifting double bonds to make alkynes, stuff like that. I am going to draw out 3 more of these for you guys to do on your own. We're going to go through the first 2 of them in class, and then the last one I'm going to let you guys take home, and then we'll do it together at the beginning of class on Monday. So you can just write in on these. You can write in base. You can write in like small base or large base. I don't need you to specify exactly which one you're using. Someone asked that in the chat. So these kind of go in order from easiest to hardest. This first one's only a couple of steps. The next one's gonna be a few more. And they're gonna kind of build off each other. Okay, I'm gonna give you guys about 5 or 6 minutes. To go through and do these, and then we're gonna go through the first 2 of them together. All right, so I'm going to start with this first one, which is actually pretty forgiving. Really, as long as you don't reduce first for this one, you're going to be fine. So trying to put our starting material into our product. This triple bond, most likely going to be this double bond here, which means we need to alkylate twice once on either side. So I'm going to do the left side first. You could do the right side first. Doesn't really matter. So I'm going to add this 3 carbon side on the left. So Na, NH2, 3 carbons here. So draw it in teal to make things a little easier. Now this would fit here. We need to add our right side. NaNH2 again. Got a 6-membered ring and a carbon and a leaving group. This way. This gives us the full carbon skeleton of our final product. So from here, we just need to add in H2 and LIN-LARs in order to make that cis double bond. And we can do our synthesis. Any questions on this one? Okay, our other one is going to be a little bit more complicated. We're going to have to build an alkyne and then do an alkylation. So looking at our starting material, we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So most likely this is our starting material. We need to add 1 more carbon at some point. We're going to have to make an alkyne. There's kind of 2 different ways you can do this. So for this first step here, you could either brominate or chlorinate. I'm going to go through the bromination pathway, but then when we get to a certain point, I'm going to show you how you could do it in 1 step through chlorination. So if I was to just throw in Br2 and light, we would brominate on this tertiary position. If we add in a small base, we could make a double bond, and then throwing in HCl, peroxide, gets us to this Cl on a secondary position. We also could have just thrown in Cl2 and light. This would have done the exact same thing here. This is actually the exact molecule we were using when we did the radical reactions and we did all that math. And we showed that this is the position that Cl2 will add to and give you the major product for. Doesn't always work out like that, but in this case, we specifically know that it will add to this position, so we could skip those steps if we wanted to. From here, we need to turn a Cl2 or Cl into a triple bond. So throwing in a large base, can put our double bond here, Br2, let this dibrominate, we can dieliminate, And then from this point, all we have to do is calculate and get to our final product. So you'll find the more you do these, the more you'll kind of get used to this. Someone in the chat asked, how do we know when we use a small base versus a large base? So you use a small base when you want to eliminate from your more substituted position. So for this one here, you're pulling off a beta proton. You have 6 of them that are on a primary center, 1 of them that is on a secondary center. So a small base is going to pull off your more substituted position. This is secondary, primary, primary. For this one here, you have a tertiary center and a primary center. A large base is going to be selective for your tertiary center. Or sorry, your primary center, it's large, it's bulky, it's not going to get to the tertiary center. So that's going to pull off here. And yes, you can just say large base, small base on the exam. I'll have you guys do more specific things later on, but for exam 1, you don't need to worry about that. So, kind of using what we did in these 2 examples, go back over the weekend and try to do that 3rd example, and we will go through it on Monday.